I'm really excited for the next speaker, who's Andrew Yates. He's currently an assistant professor at the University of Amsterdam. He previously got his PhD at Georgetown University, sorry. And also spent a couple of years at the Max Planck Institute of Informatics. So please, warm welcome for Andrew.
So let me get started. It's great to be here. My name is Andrew Yates, as Sergi just said. I'm going to try to talk about something a bit controversial today. Hopefully it turns out that way. That was my intention. So this is the role of domain knowledge in the era of transformers. So first, something I think that's been established pretty clearly so far. Transformers work really well. In this talk, I'm talking about search specifically. So here I'd say they work really well for search. So this is a plot of various models on a common benchmark. The exact numbers don't matter. The y-axis is the metric. Higher is better. So you see that regardless of the model, there are many attempts on this data set. Some models do better, some do worse. Neural models tend to do maybe a bit better than prior traditional models. But then we got transformer-based models up here. And these are a big improvement, right? So you see immediately we're doing much better than all the previous neural and the pre-neural methods that existed, or at least the results were reported. And we see something similar on MS Marco, as other talks have hinted at. I won't spend a lot of time on this. There was a neural method that did not use transformers that was state of the art on this data set, January 2019. Rodrigo, a later speaker, submitted a BERT-based method to this data set, to this leaderboard. And immediately there was a 25% improvement, just going from whatever was working well in the neural scenario to with a transformer-based model. So I think it's clear that transformers work really well. Several speakers have said, hopefully you're convinced. Part of this, they automatically learn what to capture. So we previously had to actually think even about what sort of signals we would want to capture when we're performing search. So for example, if we want to know how important a term is, we have to capture that in some way. So if we are saying is the a more discriminative term than transformer, we needed some way to quantify whether we're happy or matching the in our query or happy or matching, say, transformer in our query. A lot of ways to do this. It has to deal with how many terms the document appears in. This is inverse document frequency. The formulas for doing it aren't so important. My point is just that even knowing that this is what we want, that we want to count the number of documents a term appears in, there are many different ways to do it. Or similarly, maybe want to ask how important a term is to a document. Again, many different ways to count terms in a document. We can take a raw count, we can take 1 plus the log count, we can try to normalize it by the length of the document or by the most common term in the document, et cetera, et cetera. So there's a lot of ways to do that. Transformers figure out how to capture the signals. One final example to make this a bit more abstract. So let's think about how we might incorporate the influence of nearby terms. So something like BM25 doesn't consider nearby terms at all, right? We're only looking at unigram matches. But with another model, something like a transformer or maybe a later pre-neural model, we're trying to capture position. Well, when we capture this influence of terms that are around the term of interest, there are a lot of things we have to think about. We have to think about what nearby means. We have to think about what it means to be related to this term. We have to think about how to determine that type of relation, et cetera, et cetera. But with transformers, we can just automatically handle the scenario. We can automatically, give it a bunch of input, and it can figure out what sort of signal is useful there for understanding what to make of the proximity of terms, what to make of the situation where we see a lot of query terms near each other or very far apart. So this brings us to the question of what do we do with all this knowledge, right? So we were previously capturing all these signals. There's a long line of work, many different models where people have proposed incorporating these signals into a model, capturing them different ways. So what do we do now? Do we just try to scale everything up? So some of us go off and annotate data, maybe a few of us go off and make models, and then everyone else forgets about these signals, and then this is how we improve. So that's one option, and actually maybe making bigger models is a good way forward, right? But it's not the only way forward. And so what I want to do in this talk is talk about other ways that domain knowledge can interact with transformers, how we can use these sort of considerations that we know are important for IR, even though we're now in this world where we're not worrying about specific signal types. We don't have a lot of room to play even inside the transformer architecture. We're applying the transformer to a problem that we understand somewhat well. So in the first part of the talk, I'll divide this into three sections. We'll talk about applying transformers. In the second, evaluating transformers. And the third, what we can learn from transformers about the sort of signals we capture. So to start with, I probably don't even need to give you a refresher, but this is a transformer encoder layer. At the bottom, we have some input. At the top, we have some output. For every term that we input, we get an output, right? So we can say this is a contextualized embedding. So how this transformer encoder works is you could say it rewrites or it enriches or it somehow modifies the input embeddings we give it. So an immediate question occurs when we want to apply this transformer architecture in practice. The issue we have is that the way this architecture is designed, there's always some limit on how long the input can be. So we can pass in, maybe 512 tokens with BERT, maybe 2048 with something like GPT-3, but there's always a limit on this maximum. So then this asks the question, if we want to apply transformers to IR, how do we deal with these limitations of input length? So a straightforward way to do this in a way that does work well is we can simply split the document into different passages and then score each of those passages separately. So here you see 3 different passages from the same document. They're being input into a BERT cross encoder. At the top, you see a score coming out. And so maybe you just say this document had 3 passages. The highest scoring passage in that document is the document score. So we say a document is as relevant as the most relevant passage in it. So this makes sense from what we know about evaluation also, because we would know the document would be judged relevant if there's any relevant information in it. So this is a nice straightforward approach that does work. We can handle long documents by simply splitting them into separate sections, handling each section separately, and then maybe aggregating the scores at the end. But something else we could also do, rather than looking at the scores, is try to perform aggregation somewhere earlier. So rather than taking the maximum score, maybe we're looking at some of these embeddings or some of these other intermediate representations inside the model. So I just said that this max score approach worked well. Why would we want to do this? Well, we also know from the domain that the total amount of relevant information in the document is important, right? A document with 1 sentence related to the query is not nearly as good, probably, for the user as a document that's entirely about the query. The latter probably gives you a lot more information on your information need. So this does affect ranking. The more relevant information, the better. And ideally, we'd like to consider this in the score. So quickly, 2 ways some of my students have proposed for handling this. The first is we simply take the term embeddings from BERT. We can take separate term embeddings from every passage we process with BERT. We can combine them together, and then we can process them with some sort of pre-BERT neural model. The details of how these pre-BERT neural models don't really matter a lot. This is more detail than I want to get into in the talk. But essentially, they compare the similarity between query terms and document terms. This gives you a matrix, a similarity matrix, and then this matrix is consumed in some way. The second thing we can aggregate are passage representations. So rather than concatenating all the embeddings together, maybe we take this CLS vector from every passage and do something with it. I've simplified this. I don't want to spend a lot of time on different things we could do with it. This is also parade work with my students. But for example, we could take the max feature value. So across every dimension of the CLS vector, we could take the max, or maybe we say it's transformers all the way down, and we add some more transformer layers to try to combine these CLS tokens into a score. The point I'm making, though, is that these ways to apply transformers matter a lot, and it doesn't involve modifying the transformer architecture itself. So on the left here, you see those maximum score approaches. They work really well. I showed this at the beginning and said these are outperforming prior work. But we also see that if we're looking at the whole document, if we're trying to incorporate this context, we do better still. So those 3 dots at the top, 2 of them are looking at the whole document by incorporating context, either via terms or passages. And the other dot is using a much, much larger model. So roughly 30 times larger. I think Rodrigo will talk about this model. It's his 3 billion parameter mono T5 for re-ranking. So the point here, we arrive at about the same result, at least according to this data set, according to this metric, but we got there in 2 different ways, right? We could make the model bigger. I think this is a good direction to take. I would like to have bigger models I could consider. But also we can think about the underlying problem and try to incorporate more context, more of the document, and we also do better, right? So we're about matching the performance of this much bigger model. So now I'd like to talk about evaluating transformers. This next sections are slightly shorter. So here, the idea is that we want to understand where transformer models are failing. So we saw these test collections in previous talks, things like MS Marco and Trek Deep Learning, which are new judgments for MS Marco type queries. And so, is it the model working well across all these queries? Are there shortcomings that exist that should be addressed? So to do this, this is work with Jeff Dalton, Ian Mackey from Glasgow, SIGIA resource paper. So we look at the queries in these benchmarks and look at the performance of various models on them. So it turns out that there's just a lot of types of queries that are really easy for transformers for all these models that are being evaluated. Things like definitions. If I ask you the definition of a word, this is quite easy. If simple factoid question answering. So if I ask you like a celebrity's net worth, you could answer that in maybe 2 words, right? A number and then million, billion, 100,000, whatever. It's a fairly simple question, or like an easy description. So this is like the definition query. Models do really well on these. We also looked at where models don't do really well. So for example, if a query is ambiguous, I don't tell you which Robert Gray I'm interested in, and there's no context to inform you, then the models aren't going to perform very well because they may not pick the right Robert Gray to retrieve. If we have local queries, again, models may not perform well just because they may default to the wrong location. This query is about a cost. We don't know the location, so we don't have any idea of any specifics for calculating the cost. We also don't even know what currency the person is asking for. Maybe dollars because it's MS Marco, it's probably US data, but we don't know, and this will affect models, whether they assume it's one setting or another. The interesting queries, I would say, are those at an intersection. So these are both hard, but they're interesting because they deal with more complex topics. So either maybe comparing multiple entities is one example here at the top, or maybe some sort of complex reasoning. So it's not actually clear, I've found out from looking at this query, what the prohibition in the US did to crime. So depending on how you measure and what arguments you make, people just disagree. So there's no straightforward answer actually to this question. At least without consulting a history PhD, as far as I can tell. So we looked at what makes queries easy, what make them hard. I'll mention very briefly a few things we found. So for example, non-factoid, like I showed you on the previous slide, requires more than a single passage. So if you have a single passage, it's possibly much easier. It could indicate that the information need is less complex, or it may just be easier for the model because you're only comparing it to one section of text. So this was a good signal. And then of course, things like whether there's sufficient context, we would say query is ambiguous and discard it if there's not, etc. This comes with various annotations. I won't go through all these types in details, but we give the query types, the search engine result pages, the type of search engine result page that Google returns, etc. along with these. And so what we end up with is some subset of the 2 years of Trek Deep Learning that looks a bit different. So we go from say 41% factoid queries to 8% factoid queries. This is the biggest decrease. I think this is fairly intuitive. These are very easy to answer. These are reasonably well solved by the existing methods. They're not what we're interested in. Things like lists increase, long answers increase, web search increases a bit. Web search just means that essentially Google doesn't know what to show you. So Google is showing you the web search results rather than giving you a pane that answers the question directly, which I think is probably a good signal that it's something that would be difficult to answer with a short answer. And the interesting thing here is we do this, we reevaluate all the systems that appeared in Trek, and we see some swaps in the system ranking. Now, I'm not going to argue that the system ranking we get from this is better than the original system ranking. In fact, if I had to choose one or the other, I think this probably has fewer judgments, so maybe the original. But we see a lot of changes, right? If we remove some queries from the evaluation, if we combine queries from the 2 years focused on the behaviors we want to evaluate, we see, for example, a system in the middle, rank 13, moves towards the top. We see, for example, the top ranked system moves down a few slots. We see, at the bottom, there's some minor movement, but this is kind of encouraging because it seems reasonable that bottom ranked systems would remain, around the bottom roughly, and so on. So here we've looked at what sorts of queries transformers are not performing well on, and this kind of hints towards ways we can improve. So for example, it seems like entities are a major issue here. They're definitely entities that are not known by BERT. Perhaps comparing different entity types are hard, et cetera, et cetera. But this complex reasoning and multiple interacting entities seems like a key point that makes queries difficult. So finally, I'd like to end with something like a brief, maybe controversial proposal. So my proposal, consulting transformers, I started with these slides about different signal types, right? So I showed you there's different ways to capture TF, there's different ways to capture IDF. There's some way to capture what it means for terms to be near each other, but I'm not even sure how to formulate exactly what I want to capture there, but clearly, intuitively, it should be important. My proposal is to turn things around. So we have these transformers that are very good at ranking. Why don't we treat that transformer as an oracle and ask it, which approach here is better? When we capture the proximity of terms, should we capture it this way or that way, for example? So the idea is perhaps we can improve by taking the fact that transformers are effective and trying to look at exactly how they're effective, how this relates to signals we found in the past to be important. So I'll give you a few brief examples of this. There are two really different flavors of positional information. I try not to go into much detail here, but the top one is a SIGIR, I think 2005 paper. They look at short windows. So they have something like ordered windows of maybe 5 terms and unordered windows that are a bit bigger, I think something like 8 terms, and they try to match within that window. So if you get a lot of query terms within a small window, this is good. If not, it doesn't increase your score. The second paper is a very, very different flavor of this positional information. This is looking at the whole document and trying to kind of find the smallest distance between all query terms. So it's basically trying to measure, is there like a region of the document where all the query terms appear? Or is a query term at paragraph 1 and then another query term in the middle and then another query term at the end, this kind of thing. So you see these are totally different ways of capturing these signals. These have both been proposed. We could ask, for example, what is more like what a transformer does? So this helps us to better understand this prior work, but also it points to changes we can make to the transformer or how we apply it. So for example, all-to-all attention, this is every input is compared to every other input. This is the default. Whereas there's another approach with efficient transformers where we have local attention, where this is we only compare terms within a small window. So you see local attention is something like that first paper, all-to-all attention is something like the second. And so these notions of proximity clearly map to these ideas about signals we've seen before. So we could ask, for example, which is better? Do we really need global attention? Can we reduce the window size for local attention, et cetera? So what do we know exactly about how we're capturing this type of signal? And realistically, probably the type of signal, almost certainly the type of signal the transformer is capturing here is neither one of these papers, right? I would be amazed if it exactly correspond to either signal type. But these are a guide to illustrating the different possible ways the signal could be explored, helping us think about how a transformer might be capturing it. Another really quick example, this came up earlier, I think, in one of the questions. So there's two possible things a transformer could be doing when we're talking about soft matching, right? So it could be reducing false positives. So meaning if I say, I want to find a bank and withdraw money, I should not receive a result that talks about a riverbank, right? This is a false positive, bank matches bank, but they're used in different senses. So maybe it's dealing with the sense mismatch, maybe that's helping a lot, or maybe it's dealing with the false negatives, right? Maybe it's seeing that these systems are heavily related. If I said bank, then I would be very happy with this search term that says ATM, right? Some false negative soft match. Instead, in practice, probably both contribute to performance, but I doubt they're both 50-50, right? So what matters? And does it depend on the data? Is it dependent on the task? Like how do these types of signals we know about interact with how the transformer is performing? So this brings me to the end of the talk. So I propose this direction. I call it consulting transformers. Potentially, maybe this sort of thing can help us better understand the problems to the extent where we would ask for a new architecture. Maybe, I don't know. Maybe it's too optimistic, but there's some potential here, right? To use a less flexible architecture and maybe get some efficiency or effectiveness gains by better understanding. Even if not, though, even if that is too optimistic, practically, this has a lot of consequences for how we apply transformers. So if we knew, for example, that local attention is what mattered, then we would use something like that efficient transformer. We'd make some modifications so the query attention is okay. We would maybe think about the window size, but we wouldn't rely so much on all attention. Whether or not that's actually needed, I don't know. But you can see this clearly can affect many stages of the pipeline. In terms of data, you might wonder, whether false positive or false negatives matter more. This might affect the sort of data you use to train, the types of entities in your data might affect things, etc. So just to conclude, I'd like to give the takeaway message that it's so important to consider how we're using transformers and to think about whether we're missing ways to improve and exactly what we're measuring. So in addition to this, what can transformers tell us about prior work? So we knew about all these signals. What can we learn from them, given this oracle, so to speak, that we can query? Quick open question. I showed you this long document handling. These approaches aren't going to work for dense retrieval because you don't know the query early enough. With dense retrieval, you cannot create, you would have to create a document representation that has not, that cannot attend to the query, which means you're potentially cramming, thousands of tokens into a single vector, a small vector. There's work that suggests this is not going to work. So finally, I'd like to plug my survey at the end. This is work with Rodrigo, who'll be giving a talk shortly, and Jimmy Lin from Waterloo, pre-trained transformers for text ranking and beyond. If you're interested in text ranking, applications of transformers to this task with re-ranking or dense retrieval, feel free to check it out there. So thanks, that's everything. Can take questions.
Great, thank you. So, do you have any questions? I see a couple of hands raised in the back. Incoming.
Thank you for a nice comprehensive talk. You were mentioning like splitting the documents into some parts, or even later splitting the text into some subtokens or whatever. And have you any research on like some kind of pooling methods? In retrieval, it's quite popular to use gem pooling, generalized mean, and it also shows like the exact positions of some tokens which are the most relevant to the query. And if it has any connection to this attention matrix, so you're also mentioning maybe it can be combined all together to improve the score. What do you think about it?
Yeah, no, that's an interesting comment. To make sure I understood correctly, generalized mean pooling, you're suggesting to combine the passage scores, right? I haven't tried that. People have looked at a lot of other score pooling approaches. The ones people have looked at don't seem to help. It seems to be that actually comparing parts of the document is where some of that improvement comes from. But I don't know about this pooling specifically.
Great, I think we had another one. Can you come back a bit?
So you visualize the effect that the transformer was having on the data to understand what the transformer was doing, and you use this to improve the experiment. So do you think that more visualizations about what the transformer is doing will help you know what to do?
Yes, if it was the right visualization. It's very difficult to visualize this though, because people explore this, I think, a lot when BERT was first published. And there are just so many attention heads and so many attention layers that it's quite difficult to know what to look at. So I would say, yes, this is interesting. It's good to visualize these things. But in terms of BERT, there's the question of what exactly to visualize to understand what's going on. And as far as I'm aware, we don't know where to look exactly.
Great. So again, for the sake of time, I'm sorry we cannot have more. One quick question. Yeah, that's good. But if you get hungry, don't blame me. Yeah.
When you do the text ranking, do you train it supervised or unsupervised?
We train it supervised. Yeah.
Okay.
Great.